Okay, so what I'm going to do is I'm going to solve the three practice frame problems for you. The machine problems are very, very straightforward. It's a simple matter of taking the machines apart and solving the equilibrium equations. But the frame problems take a little bit more doing. So let's take a look at problem one. All right, that says the frame is used to support a load of sand that weighs 70 pounds. The sand hangs from a cable that passes around a frictionless pulley. The cable has a radius of 1/2 foot at D and is anchored to the wall. All right, the structure is rigidly attached to the wall at C and pinned connections A, B, D, and F. All right, so the question is find the reactions at C and the tension in the cable. We'll do that first. And then it says determine the forces at A and the forces that are in link BE. All right, so we want to determine the reactions at C, the cable tension. Well, the cable tension's obvious, right? Hopefully, anyway. The cable tension's obvious. It's equal to 70 pounds. And then we want to determine the forces acting at the pin A and at the pin E. Okay. So first thing we'll do is we'll solve the first part of the problem to determine the reactions at C. Okay. So C is a fixed support. This first thing I do is I draw my free body diagram of the entire frame. Okay, looking something like this. Again, this is not to scale. Something like this. Okay, here's the pulley. So here's the cable tension T. Here's the cable tension T. Here is CY. Here is CX. Okay. All right. So if we put some dimensions on here, this is 5.5 feet. Don't forget to include the radius of the pulley. Okay. This dimension is 2 feet. Okay. All right. And so I'm not labeling all the points, but you get that. So C is a fixed support. So I also have a reaction moment. So I'm going to assume the reaction moment is going in this direction. Okay. So there's my free body diagram of the entire frame. So again, T is equal to 70 pounds. Okay. So this is what we've got. Okay. So put my axes on here, Y and X. All right. So 3 equations of equilibrium. Sigma Fx is equal to 0. That's just T plus Cx is equal to 0. Okay, move this out of the way. So T plus Cx is equal to 0. So Cx is equal to minus T. T is 70 pounds. So Cx is minus 70 pounds. Again, the negative sign simply means, as always, it's going in the opposite direction to what I assumed on the free body diagram. Okay. Sigma Fy is equal to 0, so I get minus T plus Cy is equal to 0, so Cy is equal to T is equal to 70 pounds. Okay, so there's the 2 components of the reaction force at C. Let me tear this off. Okay, and now I do my moment equation. I'm going to do the moment about, let's see, I did the moment about C. All right, moment about C. There is no moment caused by CY or CX. So what I have is I have a moment caused by this tension. I have a moment caused by this tension. And of course, I have the reaction moment. So I'm assuming counterclockwise is positive. So I have MRC, okay, minus T times 2. That's the moment caused by this cable tension. And then I have plus T times 5.5 is equal to 0. T is equal to 70. A little bit of arithmetic. I get MRC is equal then to minus 245 pound-feet. Okay, so that answers part A. There's the reactions at C. Okay, so the next question then, or part B, is determine the forces at A and the forces at link BC. And if I look at this, Okay, there's a pin at B, a pin at E. There's no other loads acting on it, so BE is a two-force member. Always recognize a two-force member, all right? And so what I do is I say, well, if I need to determine the forces at A and the forces in link BC, I just need to draw a free body diagram and do equilibrium analysis on member ABC. Okay, so let me do that. Draw my free body diagram. Let me fold this up for a second. All right. So here is my free body diagram then of ABC. All right. So here is AY. Again, I'm making an assumption that they're going in this direction. There's AY and AX. I have FBC. I'm assuming it's vertically upward. Again, you can assume whatever you want. And then CYCX to be consistent with the directions that you have on your free body diagram of the entire frame. So here's CYCX and MRC. Okay. Looking at the dimensions, again, this not a complete free body diagram, but you have to have the complete one, obviously, on your exam. So there's 3 feet. Okay, so there's my free body diagram of member A, B, C. All right, so this is B, this is C, and this is A. Yeah. Okay. 3 unknowns, AY, AX, and FBE, because I already solved for CY and CX. All right, so sigma F X equals 0, AX plus CX is equal to 0. All right, so AX is equal to minus CX. So AX, going back to what we already solved, okay, CX is minus 70. So AX is equal to minus CX. So AX is equal to 70 pounds. AX. Right, so now I know AX, so I need to know AY and FBE. The summation in the Y direction just gives me the relationship between AY and FBE. So what I'm going to do is I'm going to take the moment. I could either take the moment about A and solve for FBE, or I could take the moment about B and solve for AY, and then use the Y equation to get the other one. So what I did was, again, makes no difference. I summed around A. All right, so there's a moment caused by FBE counterclockwise, which I've assumed to be, or if I taken to be positive, I would define to be positive. So FBE times 4, CY times 7. Okay, plus MRC is equal to 0. Okay, so I solve this equation. CY, we already know. CY is 70. Okay, so I have FBE times 4 plus 70 times 7 plus MRC, which was minus 245. Okay, so let me put the numbers in. Again, MRC was negative 245. All right, so I solve for FBE. Okay, do the arithmetic, comes out to be minus 61.25 pound-feet. Okay, so we have that. All right, and then last but not least, sigma Fy is equal to 0, says AY plus FBE plus CY is equal to 0. I put in the numbers and I get AY is minus 8.75 pounds. Okay, so I solved the problem. Okay. So again, it's very important to understand the negative signs or positive signs, the arithmetic signs in front of the answers depend on what you assumed to be the direction. So for example, if I would have assumed on my free body diagram that AY was in the negative direction, my axis on here. If I assumed it was in the negative direction, then the value of AY, the numerical value would be the same, but AY would be positive 8.75. Okay, so that solves problem number 1, frame problem number 1. Okay.